7. The p block elements. In class 11th, you have learned that the p block elements are placed in group 13 to 18 of the periodic table. Their valence shell electronic configuration is ns2 and p126, except helium, which has 1s2 configuration. The properties of p block element, like that of others, are greatly influenced by atomic size, ionization enthalpy, electron gain enthalpy, and electronegativity. The absence of d orbital in second period and presence of d or d and f orbital in heavier element starting from third period onwards have significant effect on the properties of element. In addition, the presence of all the three types of element, metals, metalloids, and non-metal, bring diversification in chemistry of these elements. Having learned the chemistry of element of groups 13 and 14 of the p block of periodic table in class 11th, you will learn the chemistry of the element of subsequent group in this unit. Group 15 elements. Group 15 include nitrogen, phosphorus, arsenic, antimony, and bismuth. As we go down the group, there is a shift from non-metallic to metallic through metalloidic character. Nitrogen and phosphorus are non-metal, arsenic and antimony metalloids, and bismuth is a typical metal. Occurrence. Molecular nitrogen comprises 78% by volume of the atmosphere in the earth crust. It occurs as sodium nitrate, NaNO3, and potassium nitrate. It is found in the form of protein in plants and animals. Phosphorus occur in minerals of the epiphyte family. Ca9PO46.CaX2 X is equal to FCl or OH, which are the main component of phosphate rocks. Phosphorus is an essential constituent of animal and plants matter. It is present in bones as well as in living cell. Phosphoproteins are present in milk and eggs. Arsenic, antimony, and bismuth are found mainly as sulfide minerals. The important atomic and physical properties of this group's element along with their electronic configuration as given in table 7.1. Trend of some of atomic, physical, and chemical properties of the group are discussed below. Electronic configuration. The valence shell electronic configuration of these elements is ns2 and np3. The s orbital in these elements is completely filled and p orbitals are half filled, making their electronic configuration extra stable. Atomic and ionic radii. Covalent and ionic radii increase in size down the group. There is a considerable increase in covalent radius from N to P. However, as from AS to Bi, only a small increase in covalent radius is observed. This is due to the presence of completely filled d and or f orbital in heavier members. Ionization enthalpy. Ionization enthalpy decreases down the group due to gradual increase in atomic size. Because of the extra stable half-filled p orbital electronic configuration and smaller size, the ionization enthalpy of the group 15 element is much greater than that of group 14 element in the corresponding period. The order of successive ionization enthalpies are expected is delta I H1 smaller than delta I H2 smaller than delta I H3. Electronegativity. The electronegativity value is in general decrease down the group with increased atomic size. However, amongst the heavier element, the difference is not that much pronounced. Physical properties. All the elements of this group are polyatomic. Dinitrogen is a diatomic gas, while all the other are solid. Metallic character increase down the group. Nitrogen and phosphorus are non-metal. Arsenic and antimony metalloids are, and bismuth is a metal. This is due to decrease in ionization enthalpy and increase in atomic size. The boiling point in general increase from top to bottom in the group, but the metallic point decrease up to arsenic and then decrease up to bismuth. Except nitrogen, all the elements show allotropy. Chemical properties. Oxidation state and trend in chemical reactivity. The common oxidation state of these elements are -3, +3, and +5. The tendency to exhibit -3 oxidation state decrease down the group due to increase in size and metallic character. In fact, last member of the group Bismuth hardly form any compound in -3 oxidation state. The stability of +5 oxidation state decrease down the group that the only well characterized Bi compound is BiF5. The stability of +5 oxidation state decrease and that of +3 state increase down the group. Nitrogen exhibit +1, +2 and +4 oxidation state also when it react with oxygen. Phosphorus also show +1 and +4 oxidation state in some oxo acids. In the case of nitrogen, all oxidation state from +1 to +4 tend to disproportionate in acidic solution. For example, 3HNO2 gives HNO3 plus H2O plus 2NO. Similarly, in case of phosphorus, nearly all the intermediate oxidation state is disproportionate into +5 and -3 both in alkyl and acid. However, +3 oxidation state in case of arsenic, antimony and bismuth become increasingly stable with respect to disproportionation. Nitrogen is restricted to a maximum valency of 4 since only 4 orbitals are available for bonding. The heavier elements have vacant d orbital in the outermost shell, which can be used for bonding and hence expand their covalence as in PF negative 6. Anomalous properties of nitrogen. Nitrogen differ from the rest of the member of this group due to its small size, high electronegativity, high ionization enthalpy and non-availability of d orbital. Nitrogen has unique ability to form p-pi multiple bond with itself and with other element having small size and high electronegativity. Heavier elements of this group do not form p-pi bond as their atomic orbital are so large and diffuse that they cannot have effective overlapping. Thus, nitrogen exists as a diatomic molecule with the triple bond between the two atoms. Consequently, its bond enthalpy is very high. On the contrary, phosphorus, arsenic, and antimony form single bond as PP, AS, and SbSb, while bismuth form metallic bond in elemental state. However, the single NN bond is weaker than the single PP bond because of high interelectronic repulsion of non-bonding electron owing to the small length. As a result, the catenation tendency is weaker in nitrogen. Another factor which affect the chemistry of nitrogen is the absence of d orbital in its valence shell. Besides restricting its covalency of 4, nitrogen cannot form d pi p pi bond as the heavier element can. Example R3p is equal to O or R3p is equal to CH2. Phosphorus and arsenic can form d pi bond also with transition metal when their compounds like P C2H5 bracket close 3 and AsC6H5 bracket close 3 act as ligand. Reactivity toward hydrogen. All the elements of group 15 form hydrides of the type EH3 where E is equal to N and P, A, S, S, B or Bi. Some of the properties of these hydrides are shown in the table 7.2. The hydrides shown regular gradation in their properties. The stability of hydride decreases from NH3 to BiH3, which can be observed from their bond dissociation enthalpy. Consequently, the reducing character of hydrides increase. Ammonia is the only a mild reducing agent while BiH3 is the strongest reducing agent amongst all the hydrides. Basicity also decrease in the order of NH3 is greater than PH3, PH3 is greater than ASH3, greater than SbH3, greater than equal to BiH3. Reactivity toward oxygen. All the elements form two types of oxides, E2O3 and E2O5. The oxide in the higher oxidation state of the element is more acidic than that of lower oxidation state. Their acidic character decreases down the group. The oxides of the type E2O3 of nitrogen and phosphorus are purely acidic, that of arsenic and antimony at amphoteric, and those of bismuth predominantly basic. Reactivity towards halogens. These elements react to form two series of halides, EX3 and EX5. Nitrogen does not form pentahalide due to non-availability of the d orbital in its valence shell. Pentahalides are more covalent than trihalides. All the trihalide of these elements except those of nitrogen are stable. In case of nitrogen, only NF3 is known to be stable. Trihalides except BiF3 are predominantly covalent in nature. Reactivity toward metals. All these elements react with metal to form their binary compounds, exhibiting -3 oxidation state such as Ca3N2, Ca3P2, Na3As2, Zn3Sb2, and Mg3Bi2. Dinitrogen preparation. Dinitrogen is produced commercially by the liquefaction and fractional distillation of air. Liquid dinitrogen distills out first, leaving behind liquid oxygen. In the laboratory, dinitrogen is prepared by treating an aqueous solution of ammonium chloride with sodium nitrate. Small amount of NO and HNO3 are also formed in this reaction. These impurities can be removed by passing the gas through aqueous sulfuric acid containing potassium dichromate. It can also be obtained by a thermal decomposition of ammonium dichromate. Very pure nitrogen can be obtained by the thermal decomposition of sodium or barium oxide. BaNH3 bracket close to gives Ba plus 3NH. Properties. Dinitrogen is a colorless, odorless, tasteless, and non toxic gas. Nitrogen atom has two stable isotopes, 14N and 15N. It has a very low solubility in water and low freezing and boiling point. Dinitrogen is rather inert at room temperature because of the high bond enthalpy of 9 triple sorry enthalpy of n triple bond n bond. Reactivity, however, increase rapidly with the rise in temperature. At higher temperatures, it directly combines with some metal to form predominantly ionic nitrides and with non-metal covalent nitrides. A few typical reactions are 6I 6Li plus N2 gives 2Li3N. 3Mg plus N2 gives Mg3N2. It combined with nitrogen at about 773 Kelvin in the presence of a catalyst to form ammonia. Dinitrogen combined with dioxygen only at very high temperature to form nitric oxide NO. Ammonia preparation. Ammonia is present in small quantity in air and soil where it is formed by a decay of nitrogenous organic matter. Example, urea. On a small scale, ammonia is obtained from ammonium salt which decompose when treated with caustic soda and calcium dihydroxide. On a large scale, ammonia is manufactured by Haber's process. In accordance with Lee-Chatterley principle, high pressure would favor the formation of ammonia. The optimum condition for the production of ammonia are a pressure of 200 multiplied 10 की power 5 Pa, a temperature of 700 Kelvin, and use of a catalyst such as iron oxide with small amount of K2O and Al2O3 to increase the rate of attainment of equilibrium. The flow chart of the production of ammonium is shown in the figure 7.1. Early iron was used as a catalyst with molybdenum as a promoter. Properties. Ammonia is a colorless gas with a pungent odor. Its freezing and boiling point are 198.4 and 239.7 K respectively. In the solid and liquid state, it is associated through hydrogen bond as in the case of water, and that accounts for its higher melting and boiling point that expected on the basis of its molecular mass. The ammonium molecules is trigonal pyramidal with the nitrogen atom as apex. It has a 3 bond pair and 1 lone pair of electron as shown in the structure. Ammonium gas is highly soluble in water. Its aqueous solution is weakly basic due to the formation of OH negative ions. NH3 plus H2O give equilibrium NH4 positive plus OH negative. It forms ammonium salt with the acid. Example NH4Cl, NH4 bracket close to SO4 etc. As a weak base, it precipitates and the hydroxide of many metal from their salt solution. For example, ZnSO4 plus 2NH4OH gives ZnOH2 plus NH4 bracket close to SO4. The presence of a lone pair of electron on the nitrogen atom of the ammonium molecules makes it a Lewis base. It donates the electron pair and form linkage with metal ion, and the formation of such complex compound find application in reduction of metal ions such as Cu2 positive and Ag positive. Oxides of nitrogen. Nitrogen form a number of oxides in different oxidation state. The names, formulas, preparation and physical appearance of these oxides are given in the table 7.3. Lewis dot main resonance structure and bond preparation parameters of oxides are given in the table 7.4. Nitric acid. Nitrogen forms oxo acids such as H2N2O2 and HNO2 and HNO3. Amongst them, HNO3 is the most important. Preparation. In the laboratory, nitric acid is prepared by heating KNO3 or NaNO3 and concentrated H2SO4 in a glass retort. NaNO3 plus H2SO4 gives NaHSO4 plus HNO3. On a large scale, it is prepared mainly by Ostwald's process. This method is based upon catalytic oxidation of NH3 by atmospheric oxygen. 4NH3 plus 5O2 gives 4NO plus 6H2O. 6H2O. The nitric oxide thus formed combined with oxygen giving NO2. Nitrogen dioxide so formed dissolve in water to give HNO3. NO thus formed is recycled and the aqueous HNO3 can be concentrated by distillation up to 68% by mass. Further concentration to 98% can be achieved by dehydration with concentrated H2SO4. Properties. It is colorless liquid. Laboratory grade nitric acid contains 68% of the HNO3 by mass and has a specific gravity of 1.504. In the gaseous state, HNO3 exists as a planar molecule with the structure as shown. In aqueous solution, nitric acid behave as a strong acid giving hydronium and nitrate ions. HNO3 plus H2O gives H3O positive plus NO3 negative. Concentrated nitric acid is a strong oxidizing agent and attack most metal except noble metals such as gold and platinum. The product of oxidation depends upon the concentration of the acid, temperature and the nature of material undergoing oxidation. 3Cu plus 8HNO3 gives 3CuNO3 bracket close to plus 2NO plus 4H2O. Cu plus 4HNO3 gives CuNO3 bracket 2 plus 2NO2 plus 2H2O. Zinc react with dilute nitric acid to give N2O and with concentrated acid to give NO2. Some metals do not dissolve in concentrated nitric acid because of the formation of passive film of oxide on the surface. Concentrated nitric acid also oxides non-metal and their compound iodine is oxidized to iodic acid, carbon to carbon oxide, sulfur to H2SO4 and phosphorus to phosphoric acid. Brown ring test. The familiar brown ring test of nitrites depends on the ability of Fe2 positive to reduce nitrate to nitric oxide with react with Fe2 positive to form a brown colored complex. The test is usually carried out by adding dilute ferrous sulfate solution to an aqueous solution containing nitrate ions and then carefully adding concentrated sulfuric acid along the side of the test tube. A brown ring of a interface between the solution and sulfuric acid layers indicate the presence of nitrate ion in solution. Phosphorus allotropic forms. Phosphorus is found in many allotropic forms, the important ones being white, red, and black. White phosphorus is translucent white waxy solid. It is a poisonous, insoluble in water but soluble in carbon disulfide and glow in dark. It dissolves in boiling NaOH solution in an inert atmosphere, giving pH3. White phosphorus is less stable and therefore more reactive than the other solid phase. Under normal condition, because of angular strain in the P4 molecule where the angle are only 60 degree, the readily catches fire in air to give dense white fumes of P4O10. P4 plus 5O2 gives P4O10. It consists of discrete tetrahedral P4 molecule as shown in the figure 7.2. Red phosphorus is obtained by heating white phosphorus at 573 Kelvin is an inert atmosphere of several days. When red phosphorus is heated under high temperature, a series of phases of black phosphorus is formed. Red phosphorus possesses iron gray luster. It is odorless, non-poisonous and insoluble in water as well as in carbon disulfide. Chemically, red phosphorus is much less reactive than white phosphorus. It does not glow in the dark. It is polymeric, consisting of chain of P4 tetrahedra linked together in the manner as shown in the figure 7.3. Black phosphorus has two forms, alpha black phosphorus and beta black phosphorus. Alpha black phosphorus is formed when red phosphorus is heated in a sealed at 803 Kelvin. It is can be sublined in air and has a epic monocyclinic or rhombohedral crystal. It does not oxidize in air. Beta black phosphorus is prepared by heating while white phosphorus at 473 Kelvin under high pressure. It does not burn in air up to 673 Kelvin. Phosphine preparation. Phosphine is prepared by the reaction of calcium phosphide with water or dilute HCl. Ca 3P2 plus 6H2O gives 3CaOH2 plus 2PH3. Ca3P2 plus 6HCl gives 3CaCl2 plus 2PH3. In the laboratory, it is prepared by heating white phosphorus with concentrated NaOH solution in an inert atmosphere of CO2. P4 plus 3 NaOH plus 3 H2O gives pH3 plus 3 NaH2PO2. When pure it is non-flammable but become inflammable owing the presence of P2H4 or P4 vapors. To purify it from the impurities, it is absorbed in HI to form phosphinum iodide, which on treating with KOH give off phosphine. PH4I KOH KI H2O PH3. Properties: it is colorless gas with rotten fish smell and it is highly poisonous. It explodes in contact with trace of oxidizing agent like HNO3Cl2 and Br2 vapors. It is slightly soluble in water. The solution of pH3 in water decomposes in the presence of light, giving red phosphorus and H2. When absorbed in copper sulfate and mercuric chloride solution, the corresponding phosphide are obtained. 3CuSO4 plus 2pH3 gives 2 Cu3P2 plus 3H2SO4. 3HgCl2 plus 2pH3 gives H3P2 plus 6HCl. Phosphine is weakly basic and like ammonia give phosphinum compound with acid. Example pH3 plus HBr gives pH4Br. Phosphorus halide. Phosphorus form two types of halide, PX3 and PX5. Phosphorus trichloride preparation. It is obtained by passing dry chloride overheated with white phosphorus. It is also obtained by the action of thionyl chloride with white phosphorus. Properties: it is colorless, oily, liquid and hydrolysis in the presence of moisture. It reacts with organic compound containing OH groups such as CH3COOH, C2H5OH. It has a pyramidal shape as shown in which phosphorus is sp3 hybridized. Phosphorus pentachloride preparation. Phosphorus pentachloride is prepared by the reaction of white phosphorus with excess of dichlorine. P4 plus 10Cl2 gives 4PCl5. It can also be prepared by the action of SO2Cl2 on phosphorus. P4 plus H10SO2Cl2 gives 4PCl5 plus 10SO2. Properties: PCl5 is a yellowish white powder and in moist air it hydrolyzes to POCl3 and finally get converted to phosphoric acid. PCl5 plus H2O gives POCl3 plus 2HCl. POCl3 plus 3H2O gives H3PO4 plus 3HCl. When heated, it sublimines but decomposes on strong heating. PCl5 gives PCl3 plus Cl2. It reacts with organic compound containing OH group, converted them to chloro derivatives. Finally, divided metal on heating with PCl5 give corresponding chlorides. It is used in the synthesis of some organic compound, example C2H5Cl, CS3COCl. In gaseous and liquid phase, it has a trigonal bipyramidal structure as shown. The three equatorial PCl bonds are equivalent, while the two axial bonds are longer than equatorial bonds. It is due to the fact that the axial bond pairs suffer from more repulsion as compared to equatorial bond pair. In the solid state, it exists as an ionic solid PCl4 positive PCl6 negative, in which a cation PCl4 positive is a tetrahedral and the anion PCl6 negative is octahedral. Oxoacid of phosphorus. Phosphorus form a number of oxoacid. The important oxoacid of phosphorus with their formulas, method of preparation and the presence of some characteristic bond in their structure as given in the table 7.5. The composition of the oxoacid are interrelated in term of loss or gain of H2O molecule or O atom. The structure of some important oxoacid are given below. In oxoacid, phosphorus is tetrahedrally surrounded by other atom. All these atom acid contain at least one p double bond O bond and one POH bond. The oxoacid in which phosphorus has lower oxidation state contain in addition of p double bond O and POH bond, either PP or pH bond but not both. These acid in +3 oxidation state of phosphorus tend to disproportionate to higher and lower oxidation state. For example, orthophosphorus acid on heating disproportionates to give orthophosphoric acid and phosphine. 4H3PO3 gives 3H3PO4 plus PS3. The acid which contain pH bond have a strong reducing property. Thus, phosphorus acid is a good reducing agent as it contains two pH bond and reduce, for example, AgNO3 to metallic silver. 4AgNO3 plus 2H2O plus H3PO2 gives 4Ag plus 4HNO3 plus H3PO4. These pH bonds are not ionizable to give H positive and do not play any role in basicity. Only those H atoms which are attached with oxygen in POH form is ionizable and cause the basicity. Thus H3PO3 and H3PO4 are dibasic and tribasic respectively, as the structure of H3PO3 has two POH bond and H3PO3. Group 16 element oxygen, sulfur, selenium, tellurium and polonium constitute group of 16 of the periodic table. This is sometimes known as a group of chalcogens. The name is derived from the Greek word for brass and point to the association of sulfur and its congruence with copper. Most copper minerals contain either oxygen or sulfur and frequently the other member of the group. Occurrence. Oxygen is the most abundant of the element on earth. Oxygen form about 46.6% by mass of earth crust. Dry air contain 20.946% oxygen by volume. However, the abundance of sulfur in the earth crust is only 0.03 to 0.1%. Combined sulfur exists primarily as sulfates such as gypsum CS4.2H2O, Epsom salt MgSO4.7H2O, barite BSO4 and sulfides such as galena, PBS, zinc, blend, ZnS, copper, pyrites, CuFeS2. Traces of sulfur occur as hydrogen sulfide in volcanoes. Organic materials such as egg protein, garlic, onion, mustard, hair, and wood contain sulfur. Selenium and tellurium are also found as metal selenides and tellurides in sulfide ores. Polonium occur in nature as a decay product of thorium and uranium minerals. The important atomic and physical properties of group 16 along with electronic configuration as given in table 7.6. Some of the atomic physical and chemical properties and their trend are discussed below. Electronic configuration. The element of group 16 have a 6 electron in their outermost shell and have ns2np4 general electronic configuration. Atomic and ionic radii. Due to increase in the number of shell, atomic and diatomic radii from top to bottom in the group, the size of oxygen atom is however expectationally small. Ionization enthalpy. Ionization enthalpy decrease down the group. It is due to increase in the size. However, the element of this group has lower ionization enthalpy values compared to those of group 15 is the of this group has lower ionization enthalpy values compared to those of group 15 in the corresponding periods. This is due to the fact that group 15 elements have extra stability half-filled p orbital electronic configuration. Electron gain enthalpy. Because of compact nature of oxygen atom, it has a less negative electron gain enthalpy than sulfur. However, from sulfur onwards, the value again become less negative up to polonium. Electronegativity. Next to fluorine, oxygen has the highest electronegativity value amongst the element within the group. Electronegativity decreases with an increase in the atomic number. This implies that the metallic character increase from oxygen to polonium. Physical property. Some of the physical property of group 16 element are given in the table 7.6. Oxygen and sulfur are non-metallic. Selenium and therium metalloids, whereas polonium is a metal. Polonium is a radioactive and short-lived. All these elements exhibit allotropy. The metallic melting and boiling point increases with an increase in atomic number down the group. The large difference between the melting and boiling point of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as diatomic molecules O2, whereas sulfur exists as polyatomic molecule S8. Chemical properties. Oxidation state and trends in a chemical reactivity. The element of group 16 exists as a number of oxidation state. The stability of -2 oxidation state decrease down the group. Polonium hardly show -2 oxidation state. Since electronegativity of oxygen is very high, it show only negative oxidation state as -2, except in the case of OF2, whereas its oxidation state is plus 2. Other element of this group exit plus 2, plus 4, plus 6 oxidation state, but plus 4 and plus 6 are more common. Sulfur, selenium and therium usually show plus 4 oxidation state in their compounds with oxygen and plus 5 with fluorine. The stability of plus 6 oxidation state decrease down the group and stability of plus 4 oxidation state increase. Bonding in plus 4 and plus 6 oxidation state is similarly covalent. Anomalous behavior of oxygen. The anomalous behavior of oxygen, like other member of p block present in second period, is due to its small size and high electronegativity. Only typical example of effect of small size and high electronegativity is the presence of strong hydrogen bonding in H2O, which is not found in H2S. The absence of d orbital in oxygen limits its covalency to 4 and in practice rarely exceeds 2. On the other hand, in the case of other element in the group, the valence shell can be explained and covalence exceeds 4. Reactivity with hydrogen. All the elements of group 16 form hydride of the type H2E. Some properties of hydrides are given in table 7.7. The acidic character increase from H2O to H2TE. The increase in acidic character can be explained in term of decrease in bond enthalpy for the dissociation of He bond down the group. Owing the decrease in enthalpy for the dissociation of He bond down the group, all the thermal stability of hydrides also decrease from H2O to H2PO. All the hydride except water possesses reducing property and this character increase from H2S to H2TE. Reactivity with oxygen. All these elements from oxide from of the EO2 and EO3 types where E double bond S, Se, Te and PO, ozone and sulfur dioxide and gases, while selenium dioxide is solid. Reducing properties of dioxide decreases from SO2 to TeO2. SO2 is reducing while TeO2 is an oxidizing agent. Besides EO2, type sulfur, selenium and therium also form EO3 type oxides. Both type of oxides are acidic in nature. Reactivity toward the halogen. Element of group 16 form a large number of halide of the type EX6, EX4 and EX2 where E is an element of the group and X is a halogen. The stability of halide decrease in the order of F greater than Cl greater than Br greater than I. Amongst hexahalide, hexafluorides are the only stable halide. All hexafluoride are gaseous in nature. They have octahedral structure. Sulfur hexafluoride SF6 is exceptionally stable in steric region. Amongst tetrafluoride, SF4 is in a gas, EF4 is a liquid and TF4 is a solid. These fluoride have sp3d hybridization and thus have trigonal bipyramidal structure in which one of the equatorial position is occupied by a lone pair of electrons. This geometry is also regarded as seesaw geometry. The element accept oxygen from dichloride and dibromides. These dihalide are formed by sp3 hybridization and thus have a tetrahedral structure. They well known monohalides and dimeric in nature. Example are S2F2, S2Cl2, S2Br2, SeCl2 and SeBr2. These dimeric halides undergo disproportion as given below. 2Se2Cl2 gives to SeCl4 plus 3CSe. Dioxygen preparation. Dioxygen can be obtained in the laboratory by following ways: by heating oxygen containing salts such as chlorates, nitrates, and paramagnates; by the thermal decomposition of the oxides of metal low in the electrochemical series and higher oxidation oxides of some metals. Hydrogen peroxide is readily decomposed into water and dioxygen by catalysts such as finely divided metal and dioxide. On a large scale, it can be prepared from water or air. Electrolysis of water lead to the release of hydrogen at the cathode and the oxygen at the anode. Industrially, dioxygen is obtained from air by first removing carbon dioxide and water vapors, and then the remaining gases are liquefied and fractionally distilled to give dinitrogen and dioxygen. Properties. Dioxygen is a colorless and odorless gas. Its solubility is in water is to extent of 3.08 kilometer cube into in 100 kilometer the extent of 3.08 centimeter cube in 100 centimeter cube water at 293 Kelvin, which is just sufficient for the visual support of marine and aquatic life. It liquefies at 90 Kelvin and freezes at 55 Kelvin. Oxygen atom has three stable isotopes and molecular oxygen O2 is a unique in being paramagnetic in spite of having even number of electrons. Dioxygen directly react with nearly all metal and non-metal except some metals, like example AuPt and some noble gases. Its combination with other element is often strongly exothermic, which help in sustaining the reaction. However, to instate the reaction, some external heating is required as bond dissociation enthalpy of oxygen double bond is high. Some of the reaction is dioxygen with metal, non-metals and other compound are given below. Some compounds are catalytically oxidized. For example, 2SO2 plus O2 gives 2SO3, 4HCl plus O2 gives 2Cl plus 2H2O. Simple oxides. A binary compound of oxygen with another element is oxides. As already stated, oxygen react with most of the element of the periodic table to form oxide. In many cases, and one element form two or more oxide. The oxide vary widely in their nature and properties. Oxide can be simple or mixed. Simple oxide can be classified on the basis of their acidic, basic and amphoteric character. An oxide that combine with water to give an acid is termed acidic oxide. For example, SO2 combined with water to give H2SO3 an acid. SO2 plus H2O gives H2SO3. As a general rule, only non-metal oxide are acidic, but oxide of some metal in high oxidation state also have acidic character. The oxides which give a base with water are known as basic oxide. For example, CO combined with water to give CaOH to add a base. In general, metallic oxide are basic. Some metallic oxides exhibit a dual behavior. They show characteristics of both acid as well as basic oxides. Such oxides are known as amphoteric oxide. They react with acid as well as alkyls. For example, Al2O3 react with acid as well as alkyls. There are some oxides which are neither acidic or basic. Such oxides are known as neutral oxide. Example of neutral oxides are CONO and N2O. Ozone. Ozone is an allotropic form of oxygen. It is too reactive to remain for a long in the atmosphere to at sea level. At a high is of about 20 km is formed with the atmospheric oxygen in the presence of sunlight. This ozone layer protects the earth's surface for an exclusive concentrated of ultraviolet radiations. Preparation. When a slow dry stream of oxygen is passed through a silent electrical discharge, conversion of oxygen to ozone occur. The product is known as ozonized oxygen. Since the formation of ozone from oxygen is an endothermic process, it is necessary to use a silent electrical discharge in its preparation to prevent its decomposition. If concentration of ozone greater than 10% and are required, a battery of ozonizer can be used and pure ozone can be condensed as in a vessel surrounded by a liquid oxygen. Properties. Pure ozone in a pale blue gas, dark blue liquid, and violet black solid. Ozone has a characteristic smell and in small concentration it is harmless. However, if the concentration rises above about 100 parts per million, breathing becomes uncomfortable, resulting in headache and nausea. Ozone is thermodynamically unstable with respect to oxygen since its decomposition into oxygen results in the liberation of heat and an increase in entropy. These two effects reinforce each other, resulting in large negative gives free energy change for its conversion into oxygen. It is not really surprising, therefore, high concentration of ozone can be dangerously explosive. Due to the ease which is liberates among atoms of nascent oxygen, it acts as a powerful oxidizing agent. For example, it oxidizes lead sulfide to lead sulfate and iodide ion to iodine. When ozone reacts with excess of potassium iodide solution buffered with a borate buffer, iodine is liberated which can be titrated against a standard solution of sodium thiosulfate. This is a quantitative method for estimating O3 gas. Experiments have shown that nitrogen oxide combine very rapidly with ozone and there is thus the possibility that nitrogen oxide emitted from the exhaust system of supersonic jet airplanes might be slowly depleting the concentration of ozone layer in the upper atmosphere. Another threat of this ozone layer is probably posed by the use of pheromones which are used in aerosol sprays as refrigerants. The two oxygen bond length in the ozone molecule are identically and the molecule is angularly is accepted at the bond angle is about 117 degree. It is resonance hybrid of two main forms. Sulfur allotropic form. Sulfur form numerous allotropes of which the yellow rhombic alpha sulfur and monoclinic beta sulfur form are the most important. The stable form at room temperature is rhombic sulfur, which transforms the monoclinic sulfur when heated above 369 Kelvin. Rhombic sulfur, alpha sulfur. This allotrope is yellow in color, melting point 385.8 Kelvin, and specific gravity 2.06. Rhombic sulfur crystal are formed on evaporating and the solution. The role sulfur in SCS2. It is soluble in water but dissolved to some extent in benzene, alcohol, and ether. It is readily soluble in CS2. Monocyclic sulfur, beta sulfur. Its melting point is 393 Kelvin and specific gravity 1.98. It is soluble in CS2. This form of sulfur is prepared by melting chromic sulfur in a dish and cooling till crust is formed. Two holes are made in the crust and the remaining liquid poured out. On removing the crust, colorless needle-shaped crystal of beta sulfur are formed. It is stable above 369 Kelvin and transferred into alpha sulfur below it. Conversely, alpha sulfur is stable below 369 Kelvin and transforms into beta sulfur above this. At 369 Kelvin, both the form are stable. This temperature are called transition temperature. Both rhombic and monoclinic sulfur have S8 molecules. These S8 molecules are packed to give different crystal structure. The S8 ring in both the form is puckered, pucked and has a crown shape. The molecular dimensions are given in figure 7.5. Several other modifications of sulfur containing 6 to 20 sulfur atom per ring have been synthesized in the last 2 decades. In S6, the ring adopts the chain form and the molecular dimensions are shown in the figure 7.5. At elevated temperature, S2 is the dominant species and is paramagnetic like O2. Sulfur dioxide preparation. Sulfur dioxide is formed together with a little sulfur trioxide when sulfur is burned in air or oxygen. In the laboratory, it is readily generated by treating a sulfide with dilute sulfuric acid. Industrially, it is produced by a byproduct of a roasting of sulfide ores. The gas, after drying, are liquefied under pressure and stored in steel cylinders. Properties. Sulfur dioxide is a colorless gas with pungent smell and is highly soluble in water. It liquefies at room temperature under a pressure of 2 atmosphere and boils at 263 Kelvin. Sulfur dioxide, when passed through water, form a solution of sulfurous acid. It reacts readily with sodium hydroxide solution, forming sodium sulfide, which then react with more sulfur dioxide to form sodium hydrogen sulfide. In its reaction with water and alkyls, the behavior of sulfur dioxide is very similar to that of carbon dioxide. Sulfur dioxide reacts with chlorine in the presence of charcoal to give sulfuryl chloride SO2Cl2. It is oxidized to the sulfur trioxide by oxygen in the presence of vanadium oxide catalyst. When most sulfur dioxide behave as a reducing agent, for example, it convert iron 3 ions to iron 2 ions and decolorize acidified potassium permanganate solution. The latter reaction is a covariance test for the gas. The molecule of SO2 is angular. It is resonance hybrid of two conical forms. Oxo acid of sulfur. Sulfur form a number of oxo acids such as H2SO3, H2S2O3, H2S2O4, H2S2O5, H2SXO6, H2SO4, H2S2O7, H2S2O, H2SO5, H2S2O8. Some of these acids are unstable and cannot be isolated. These are known in aqueous solution or in the form of their salt. Structure of some important oxo acids are shown in the figure 7.6. Sulfuric acid. Manufacture. Sulfuric acid is one of the most important industrial chemical worldwide. Sulfuric acid is manufactured by a contact process which involves three steps: burning of sulfur and sulfide ore in air to generate SO2, conversion of SO2 to SO3 by the reaction with oxygen in the presence of a catalyst, and absorption of SO3 in H2SO4 to give oleum. A flow chart of the manufacture of sulfuric acid as shown in the figure 7.7. The SO2 produced is purified by removing dust and other impurities such as arsenic compound. The key step is manufacture of H2SO4 in the catalyst oxidation of SO2 with SO2 to give SO3 in the presence of V2O5. The reaction is exothermic, reversible, and the forward reaction leads to decrease in volume. Therefore, low temperature and high pressure are the favorable condition for maximum yield. But the temperature should not be very low, otherwise rate of reaction will become slow. In practice, the plant is operated at the pressure of 2 bar and a temperature of 720 Kelvin. At the SO3 gas from a catalytic converted is absorbed in concentrated H2SO4 to produce oleum. Dilution of oleum with water gives H2SO4 of the desired concentration. In the industry, two steps are carried out simultaneously to make the process of a continuous one and also reduce the cost. The sulfur acid obtained by contact process is 96 to 98% pure. Properties: sulfuric acid is colorless, dense, oily liquid with a specific gravity of 1.84 at 298 Kelvin. The acid freezes at 283 Kelvin and boils at 611 Kelvin. It dissolves in water with the evaluation of a large quantity of heat. Hence, care must be taken while preparing sulfuric acid solution from concentrated sulfuric acid. The concentrated acid must be added slowly into water with constant stirring. The chemical reaction of a sulfuric acid are as a result of the following characteristics: a low volatile, strong acidic character, strong affinity of water, and ability to act as a oxidizing agent. In aqueous solution, sulfuric acid ions in two steps. The large value of Ka1 means that H2SO4 is largely dissociated into H positive and HSO4 negative. Greater the value of dissociation constant, the stronger is the acid. The acid form two series of salt, normal sulfide and acid sulfate. Sulfuric acid, because of its low volatile, can be used to manufacture more volatile acid and their corresponding salts. Concentrated sulfuric acid is a strong dehydrating agent. Many wet gases can be dried by passing them through sulfuric acid provided the gas do not react with the acid. Sulfuric acid removes water from organic compound. It is evident by its carrying action and carbohydrates. C12H22O11 gives 12C plus 11H2O. Hot concentrated sulfuric acid is moderately strong oxidizing agent. In this respect, it is intermediate between phosphoric and nitric acid. Both metal and non-metal are oxidized by concentrated sulfuric acid, which is reduced to SO2. Group 17 elements: fluorine, chlorine, bromine, iodine, and astatine are member of group 17. These are collectively known as halogens. The halogen are highly reactive non-metal elements like group 1, 2 and 2. The element of group 17 show great similarity amongst themselves. That much similarity is not found in the element of other group of periodic table. Also, there is a regular gradation in their physical and chemical properties. Astatine is a radioactive element. Occurrence: fluorine and chlorine are fairly abundant, while bromine and iodine less so. Fluorine is present mainly in soluble fluorides, and small quantities are present in soil, river, water, plants, and bones and teeth of animals. Sea water contains chlorides, bromides, and iodides of sodium, potassium, magnesium, and calcium, but in mainly sodium chloride solution. The deposit of dried up seas contain these compound. Example: sodium chloride and carenolite KCl3 KCl.MgCl2.6H2O. Certain form of marine life contain iodine in their system. Various seaweeds, for example, contain up to 0.5% of iodine, and Chile saltpeter contain up to 0.2% of sodium iodate. The important atomic and physical properties of group 17 element along with their electronic configuration are given in table 7.8. The trend of some of the atomic, physical, and chemical properties are discussed below. Electronic configuration: all these elements have 7 electrons in their outermost shell, Ns2np5, which is 1 electron short of the next noble gas. Atomic and ionic radii: the halogen have the smallest atomic radii in their respective period due to maximum effective nuclear charge. The atomic radius is of fluorine, like the other element of second period, is extremely small. Atomic and ionic radii increase from fluorine to iodine due to increased number of quantum shells. Ionization enthalpy, they have little tendency to lose electron, thus they have high ionization enthalpy. Due to increase in atomic size, ionization enthalpy decrease down the group. Electron gain enthalpy, halogen have maximum negative electron gain enthalpy in the corresponding period. This is due to the fact that the atom of these elements have only one electron less than stable noble gas configuration. Electron gain enthalpy of these elements of a group become less negative down the group. However, the negative electron gain enthalpy of fluorine is less than that of chlorine. It is due to small size of fluorine atom. As a result, there is a strong electronic repulsion in the relatively small 2p orbital of fluorine, and thus the incoming electron does not experience much attraction. Electronegativity, they have very high electronegativity. The electronegativity decrease down the group. Fluorine is the most electronegative element in the periodic table. Physical property, halogen display smooth variation in their physical property. Fluorine and chlorine are gas, bromine is a liquid, and iodine is a solid. Their melting and boiling point steadily decrease with atomic number. All halogen are colored. This is due to absorbed earth radiation in visual region, which result in the extinction of outer electron of higher energy level. By absorbing different quanta of radiation, they display different color. For example, F2 has yellow, Cl2 greenish yellow, Br2 red, and I2 violet color. Fluorine and chlorine react with water. Bromine and iodine are only strangely soluble in water but are soluble in various organic solvent such as chloroform, carbon tetrachloride, carbon disulfide, and hydrocarbon to give colored solution. One curious anomaly we notice that table 7.8 is the smaller enthalpy of discussion of F2 compared to that of Cl2, whereas XX bond dissociation enthalpies from chlorine onward show that expected trend. Cl Br II. A reason for this anomaly is the relatively large electron repulsion among the lone pair of F2 molecule, where they are much closer to each other than in case of Cl2. Chemical properties, oxidation state and trend in chemical reactivity. All the halogen except plus minus 1 oxidation state. However, chlorine, bromine, and iodine exhibit plus 1, plus 3, plus 5, and plus 7 oxidation state, also has explained below. The higher oxidation state of chlorine, bromine, and iodine are realized mainly when the halogen are in combination with the small and highly electronegative fluorine and oxygen atom. Example, in interhalogen oxide and oxoxide, the oxidation state of plus 4 and plus 6 occur in the oxides and oxoacid in chlorine and bromine. The fluorine atom has no d orbital in its valence shell and therefore cannot expand its octet. Being the most electronegative, it exits only minus 1 oxidation state. All the halogen are highly reactive. They react with metal and non-metal to form halides. The reactivity of the halogen decreases down the group. The readily acceptance of an electron is the reason of the strong oxidizing nature of halogen. F2 is the strongest oxidizing halogen and it oxidizes other halide ion in the solution or even in the solid phase. In general, a halogen oxidizes halide ion or of higher atomic number. The decreasing oxidizing ability of the halogen in an aqueous solution down the group is evident from their standard electrode potential, which are depend on the parameters indicated below. The reactive oxidizing power of halogen can further be illustrated by their reaction with water. Fluorine oxidizes water to oxygen, whereas chlorine and bromine react with water to form corresponding hydrohalic and hydrophorous acid. This reaction is iodine with water is non-spontaneous. In fact, I negative can be oxidized by oxygen in acidic medium, just the reverse of the reaction observed with fluorine. Anomalous behavior of fluorine. like other elements of p block present in second period of the periodic table. Fluorine is an anomalous in many properties. For example, ionization enthalpy, electronegativity, and electrode potential are all higher for fluorine than accepted from the trend set by the other halogen. Also, ionic and covalent radii, melting and boiling point enthalpy of bond dissociation, and electron gain enthalpy are quite lower than expected. The anomalous behavior of fluorine is due to its small size, highest electronegativity, low FF bond dissociation enthalpy, and non availability of d orbital in valence shell. Most of the reaction of fluorine are exothermic. It form only one oxo acid while other halogen form a number of oxo acid. Hydrogen fluoride is a liquid due to strong hydrogen bonding. Other hydrogen halide are gases. Reactivity toward hydrogen. They all react with hydrogen to give hydrogen halide, but affinity of hydrogen decreases from fluorine to iodine. Hydrogen halide dissolve in water to form hydrohalide acid. Some of the properties of hydrogen halide are given in table 7.9. The acidic strength of these acids varies in order. HF smaller than HCl, smaller than HBr, smaller than HI. The stability of these halide decrease down the group due to decrease in bond dissociation enthalpy in the order. HF is greater than HCl, greater than HBr, greater than HI. Reactivity towards oxygen. Halogen formed many oxides with oxygen, but most of them are unstable. Fluorine formed two oxides, OF2 and O2F2. However, only OF2 is thermally stable at 298 Kelvin. These oxides are essentially oxygen fluoride because of the higher electronegativity of fluorine than oxygen. Both are strong fluorinating agent. O2F2 oxidize platinum to PuF6, and the reaction is used in removing plutonium as PuF6 from spent nuclear fuel. Chlorine, bromine, and iodine form oxide in which the oxidation state of these halogen range from 1 to +7. A combination of kinetic and thermodynamic factor lead to the generally decreasing order of the stability of oxide form the halogen I greater than Cl greater than Br. The higher oxidize of halogen tends to be more stable than the lower ones. Chlorine oxides Cl2O, Cl2O2, Cl2O6, and Cl2O7 are highly reactive oxidizing agent and tend to explode. Cl2O is used as a bleaching agent for paper pulp and textile and in water treatment. The bromine oxide Br2O, Br O2, BrO3 are the least stable halogen oxides and exist only at low temperature. They are very powerful oxidizing agent. The iodine oxide I2O4, I2O5, I2O7 are insoluble solid and decompose on heating. I2O5 is a very good oxidizing agent and is used in the extremation of carbon monoxide. Reactivity toward metal. Halogen react with metal to form metal halides. For example, bromine react with magnesium to give magnesium bromide. The ionic character of the halide decrease in the order of MF greater than MCl, greater than MBr, greater than Mi, where M is a monovalent metal. If a metal exits more than one oxidation state, the halide in higher oxidation state will be more covalent than one in lower oxidation state. For example, SnCl4, PbCl4, SbCl5, and UF6 are more covalent than SnCl2, PbCl2, SbCl3, and UF4 respectively. Reactivity of halogen toward other halogen. Halogen combine amongst themselves to form a number of compounds known as interhalogen of the type XX-, XX3-, XX5-, and XX7-, where X is a large size halogen and X- is a smaller size halogen. Chlorine. Chlorine was discovered in 1774 by Chiles by the action of HCl on MnO2. In 1810, Davy established its elementary nature and suggested the name chlorine on account of its color. Preparation. It can be prepared by any one of the following method: by heating magnesium dioxide with concentrated hydrochloric acid. However, a mixture of common salt and concentrated H2SO4 is used in place of HCl. By the action of HCl on potassium permanganate. Manufacture of chlorine. Second process, by oxidizing of hydrogen chloride gas by atmospheric oxidation in the presence of C2Cl at 723 Kelvin. Electrolytic process, chlorine is obtained by the electrolysis of brine. Chlorine is liberated at anode. It is also obtained by as byproduct in many chemical industries. Properties, it is a greenish yellow gas with pungent and suffocation odor. It is about 2 to 5 times heavier than air. It can be liquefied easily into greenish yellow liquid which boils at 239 Kelvin. It is soluble in water. Chlorine reacts with a number of metal and non-metal to form chlorides. It has a great affinity of hydrogen. It reacts with compound containing hydrogen for form HCl. With excess ammonium chlorine give nitrogen and ammonium chloride, whereas with excess chlorine nitrogen trichloride is formed. With cold and dilute alkyls, chlorine produces a mixture of chloride and hypochlorite, but with hot and concentrated alkenes is give chloride and chlorate. With dry slaked lime, it give bleaching powder. The composition of bleaching powder is CaOCl2 dot CaCl2 dot CaOH2 dot 2H2O. Chlorine react with hydrocarbon and give substitution product with saturated hydrocarbon and addition product with unsaturated hydrocarbon. For example, CH4 plus Cl2 gives CH3Cl plus HCl. Chlorine water on standing loses its yellow color due to the formation of HCl and HOCl. Hypochlorous acid is formed gives nascent oxygen which is responsible for oxidizing and bleaching properties of chlorine. It oxidizes ferrous to ferric and sulfide to sulfate. Chlorine oxidizes sulfur dioxide to sulfur trioxide and iodine to iodate. In the presence of water, they form sulfuric acid and iodic acid respectively. It is powerful bleaching agent. Bleaching agent action is due to oxidation. Cl2 plus H2O gives 2HCl plus O. Colored substance plus O gives colorless substance. Hydrogen chloride. It bleaches vegetable or organic matter in the presence of moisture. Bleaching effect of chlorine is permanent. Glabier prepared this acid in 1648 by heating common salt with concentrated sulfuric acid. Davies in 1810 showed that it is a compound of hydrogen and oxygen. Chlorine. Preparation. In laboratory, it is prepared by heating sodium chloride with concentrated sulfuric acid. NaCl plus H2SO4 gives NaHSO4 plus HCl. NaHSO4 plus NaCl gives N2SO4 plus HCl. HCl gas can be dried by passing through concentrated sulfuric acid. Properties. It is colorless and pungent smelling gas. It can be easily liquefied to a colorless liquid and freezes at a white crystalline solid. It is extremely soluble in water and ionizes as follows. Its aqueous solution is called a hydrochloric acid. High value of dissociation constant indicate that it is a strong acid in water. It reacts with NH3 and give white fumes of NH4Cl. NH3 plus HCl gives NH4Cl, where when 3 parts of concentrated HCl and 1 part of concentrated HNO3 are mixed, aqua regia is formed which is used for dissolving noble metal, example gold and platinum. Au plus 4H positive plus NO3 negative plus 4HCl negative gives AuCl4 negative plus NO plus 2H2O. 3Pt plus 16H positive plus 4NO3 negative plus 18Cl negative gives 3PtCl3 6 2 negative plus 4NO plus 8H2O. Hydrochloric acid decomposes salt of weaker acid, example carbonate, hydrogen carbonate, sulfides, etc. Oxoacids of halogen. Due to high electronegativity and small size, fluorine form only one oxoacid, HOF, known as fluoric acid, and hypofluorous acid. The other halogen form several oxoacids. Most of them cannot be isolated in pure state. They are stable only in aqueous solution or in the form of their salts. The oxoacids of halogen are given in the table 7.10 and their structure are given in the figure 7.8. Interhalogen compound. When two different halogens react with each other, interhalogen compound are formed. They can be assigned journal composition as XX XX3 XX5 and XX7, where X is a halogen of larger size and X dash of smaller size, and X is a more electropositive than X dash. As the ratio between radii and X dash increases, the number of atom per molecules also increase. Thus the iodine fluoride should have maximum number of atom, as the ratio of radii between I and F should be maximum. That is why its formula is IF7. Preparation: the interhalogen compound can be prepared by the directing combination or by the action of halogen or on lower interhalogen compound. The product form depend upon some specific condition. For example, Cl2 plus F2 gives 2CIF. Properties: some property of interhalogen compound are given in table 7. These all covalent molecule and are diamagnetic in nature. They are volatile, solid or liquid at 298 Kelvin except CIF, which is a gas. Their physical properties are intermediate between those of a constituent halogen, except that their melting point and boiling point are a little higher than expected. Their chemical reaction can be compared with the individual halogen. In general, interhalogen compound are more reactive than halogen. This is because X dash bond in interhalogen is weaker than XX bond in halogens. Except FF bond, all these undergo hydrolysis, giving halide ion derived from the smaller halogen and hypohalite, halate, and perhalate anion derived from the larger halogen. XX dash plus H2O gives HX dash plus HOX. Their molecular structure are very interesting, which can be explained on the basis of whisper theory. The XX3 compound have the bent T shape, XX5 compound square pyramidal, and XXI5 IF7 has a pentagonal bipyramidal structure. Table 7.11. Group 18. Group 18 consists of 6 elements: helium, neon, argon, krypton, xenon, and radon. All these are gases are chemically unreactive. They form very few compound. Because of this, they are termed noble gases. Occurrence: all the noble gases except radon occur in the temperature. Their atmospheric abundance in dry air is 1% by volume, of which argon is a major constituent. Helium and sometimes neon are found in mineral of radioactive origin. Example: pitchblende, monazite, and cleveite. The main commercial source of helium is natural gas. Xenon and radon are the rarest element of group. Radon is obtained as a decay product of 226Ra. The important atomic and physical properties of the group 18 element along with their electronic configuration are given in the table 7.12. The trend in some of the atomic, physical and chemical properties of group are discussed here. Electronic configuration: all noble gas are general electronic configuration ns2np6 except helium, which has 1s2. Many of the properties of noble gases include their inactive nature and ascribed their closed shell structure. Ionization enthalpy: due to stability electronic configuration, these gases exhibit very high ionization enthalpy. However, it decreases down the groove with increase in atomic size. Atomic radii increase down the groove with decrease in atomic number. Electron gain enthalpy: since noble gas have stable electronic configuration, they have no tendency to accept the electron and therefore have a large positive value of electron gain enthalpy. Physical property: all the noble gas are monoatomic. They are colorless, odorless, and tasteless. They are sparingly soluble in water. They have very low melting and boiling point. Because the only type of interatomic interaction of these elements is weak dispersion forces, helium has the lowest boiling point of any known substance. It has an usual property of diffusing through most commonly used laboratory materials such as rubber, glass, and plastic. Chemical property: in general, noble gas are least reactive. Their intense of to chemical reactivity is attributed of the following reason: the noble gas except helium 1s2 have a completely filled ns2 np6 electronic configuration in their valence shell. They have high ionization enthalpy and more positive electron gain enthalpy. The reactivity of noble gas has been investigated occasionally ever since their discovery, but all attempts of force them to react to form the compound were unsuccessful for few years. In March 1962, Neil Bartlett, that then at the University of British Columbia, observed the reaction of a noble gas. First, he prepared a red compound which is formulated as O2 positive, PTF6 negative. He then realized that the first ionization enthalpy of molecular oxygen was almost identical with that of xenon. He made effort to prepare some type of compound with the Xe and was successful in preparing another red color compound Xe positive, PTF6 negative by mixing PTF6 and xenon. After this discovery, a number of xenon compound mainly with most electronegative element like fluorine and oxygen have been synthesized. The compound of krypton are flavor. Only the difluoride has been studied in detail. Compound of radon has have not been isolated but only identified by radio tracer technique. No true compound of AR, Ne and ZHE are yet known. Xenon fluorine compounds. Xenon form three binary fluorine XeF2, XeF4 and XeF6 by the direct reaction of elements under appropriate experimental condition. XeF6 can also be prepared by the interaction of XeF4 and O2F2 at 443 Kelvin. XeF4 plus O2F2 gives XeF6 plus O2. XeF2, XeF4 and XeF6 are colorless crystalline solid and sublime readily at 298 Kelvin. They are powerful fluorinating agent. They are readily hydrolyzed even by trace of water. For example, XeF2 is hydrolyzed to give XeHF and O2. 2xef2 plus 2h2o gives 2xe plus 4hf plus O2. The structure of three xenon fluoride can be deduced from whisper and they are shown in figure 7.9. Xef2 and Xef4 have linear and square planar structure respectively. Xef6 have a 7 electron pair and would thus have a disordered octahedral structure are found experimentally in the gas phase. Xenon fluorides react with fluoride ions acceptor to form cationic species and fluoride ion donor to form fluoranions. XeF2 plus PF5 gives XeF positive, PF6 negative. XeF4 plus SbF5 gives XeF3 positive, SbF6 negative. Xenon oxygen compound. Hydrolysis of XeF4 and XeF6 with water give XeXO3. XeXeF4 plus 12H2O gives 4Xe plus 2XeO3 plus 24XF plus 3O2. XeF6 plus 3H2O gives XeO3 plus 6HF. Partial hydrolysis of XeF6 give oxyfluorides XeFO4 F4 and XeO2 F2. XeF6 plus H2O gives XeO F4 plus 2HF. XeF6 plus 2H2O gives XeO2 F2 plus 4HF. XeO3 is a colorless explosive solid and have a pyramidal molecular structure. XeO F4 is a colorless volatile liquid has a square pyramidal molecular structure.